Hello friends and welcome to the e-lecture series on smart grid. We are now starting unit number 2, that is smart grid technologies in substation. In this unit we are going to cover first intelligent devices, that is remote terminal unit, a block diagram and function of each block, intelligence electronic devices, phase measurement unit, then smart substations in module 2, substations and feeder automation, application for monitoring, protection and control, smart storage technologies and applications, that is battery, flow and advanced SMEs. So let's start with the module number 1, unit number 2, that is intelligent devices. In this module, we are going to cover remote terminal unit, block diagram and functions of each block, then intelligent electronic devices, phase measurement unit. So the first topic, that is nothing but the remote terminal unit. So RTUs are primarily standalone data acquisition and control units. A typical RTU configuration is shown here into the figure, which includes the hardware modules such as controlled microprocessor and associated memory, analog inputs, analog outputs, counter inputs, digital outputs, communication and I/O interfaces, power supply, together with the RTU, track and enclosure. Small RTUs are generally have fewer than 1 to 20. Small RTUs generally have fewer than 10 to 20 analog and digital signal inputs. Medium-sized RTUs have 100 digital and 30 to 40 analog signal inputs. Any RTU with more signal input than this is referred as large. Now typically a RTU serves as an intermediate entry between the control center and intelligent electronic devices on the grid, that is IED. This communication requirement for SCADA are very stringent. These includes but are not limited to extremely high ability, reliability, and information security along with a very low latency. The SCADA system is used both at the distribution level and at the transmission level. SCADA is operated by distribution companies, DISCOM, or low voltage distribution lines. SCADA is operated by the transmission system for high voltage transmission lines. A typical architecture of SCADA and DMS is depicted as below. Now here the RTUs are used to convert electronic signal received from the field instrumentation into the communication protocol that is used to transmit the data over the networks. The RTU appears in the field as a box in a sandwich board with electric signal wires running to field instrumentation and a cable linked to a communication channel interface, such as a telephone cable, a field bus, or a radio. The instruction for the automation of field data interface devices are usually stored locally since the limited bandwidth typical of communications like to SCADA central host makes central storage impractical. Such instructions are traditionally held within local electronic device known as programmable logic controllers, that is famously known as PLCs, which have in the past been physically separate from RTUs. PLCs connected directly to field instruments and incorporate program intelligent in the form of logical procedure that will be executed in the event of certain field conditions. More recent systems have no PLCs and control logic is held with the RTU or in logics relay in local switchboards. Multiple RTUs connected to an MTU increase the reliability of a system by reducing the chances of network failure, as many RTUs connected to a central control. Here all RTUs are connected to each other via central MTU directly, and each RTU has a point-to-point connectivity with MTU on individual basis. An extended or series star topology is a variant of same group in which each branch has series connection extendedly. The advantage of this connection is use of one MTU which many devices, while with the increased complexity and compromised efficiency of the system. Now let's understand modern RTU. Modern RTU is a modular architecture with advanced capabilities to support data processing functions. The modular RTU design configuration make it available for installation ranging from a small point count site such as pole mounted distribution transformer to a very large number point in a large power substation. Modern RTO modules include expandable analog input output, digital input output points, accumulated input units, and communication card with power supply. RTU installation requirements are met by assembling the required number of RTU card or rack mounted modules to accommodate the analog control, digital and communication links for the site to be supervisory controlled. The packing of the reasonable point count RTU is chosen for the distribution line requirement. The SCADA for distribution automation has the option of installing one RTU in one cabinet with connections to the substation IEDs, or installing a master RTU and number of slave RTUs at different locations within the substation and connected to the master RTU with fiber optic communications. The distributed RTU modules are integrated to a data concentrating unit which in turn communicate with the host SCADA computer system. The modern RTU can accept AC inputs from a variety of measurements, digital meter and protection devices, digital relays through a serial port. The RTU can take the measurement as hardwired from CT, potential or VT station service transformers and transducers. Direct AC input with the processing capability of the modern RTU support fault current detections and harmonic content measurements. The fault location algorithm can be embedded in RTU firmware, giving the RTU the ability to report the direction, magnitude, and duration of the fault current with time tagging of the fault event to 1 millisecond resolution. Monitoring and reporting of harmonic content in the distribution feeder also could be included into the RTU. The digital signal processing capability of the RTU supports the necessary calculation to report THD of each of the three-phase voltage and current measurement at the automated distribution feeder or substation site. The RTU configuration software can include the logic capability to support the development of control algorithm to meet specific operating requirements. The automatic transfer control scheme have been built using the automated switches and RTUs with the high processing capability. The high capability provides another benefits to the design engineer when developing the quality of service and addressing critical load concerns. The logic capability in the RTU has been used to create an algorithm to control switch capacitors for operation on the distribution feeder. The capacitors are switched on at zero voltage crossing and switch off at zero current crossing. The algorithm can be specified to switch the capacitor for various system specifications such as voltage, power factor, reactive load, and the time. The remote control capability of RTU allows the distribution operator to make control of the capacitor to meet inductive load needs. These new logic and input capabilities have allowed the modern RTU to become an dynamic device with increased processing capabilities, usage, and applications. Now let's understand the RTU structure and its various blocks like power supply, digital input, digital output, analog input, analog output, software and logic control, and communication. The RTU architecture comprises of CPU, volatile memory, and non-volatile memory for processing and storing the program data. Now, figure shows the block diagram of typical RTU configuration. A typical RTU hardware module includes control processor and associated memory and all the analog input, analog output, counter input, digital output, communication interfaces, and the power supply. So let's see one by one. The first one is the power supply. The form of power supply will be included for operation from the main. The form of power supply will be included for operation from the AC main for various CPU, status, waiting voltage, and other interface cards. This may consist of AC to DC converters where operated from a station battery system. RTU may include a battery and charger circuitry to continue operation in event of AC power failure or critical applications where a station battery is not available. Next block is digital input. Most RTUs incorporate an input station section or input status card to acquire to state real world information. This is usually accomplished by using an isolated voltage or current source to sense the position of remote contact at the RTU site. This contact position may represent many different devices, including electrical breakers, liquid valve position, alarm conditions, and mechanical position of the devices. Counter inputs are the optional. Analog inputs. A RTU can monitor analog inputs of different types including 0 to 1 milliampere, 4 to 20 milliampere current loop, 0 to 10 volt, etc. Many RTU input buffer larger quantities via transducers to convert and isolate real-time quantities from the sensitive RTU input levels. A RTU can also receive analog data via communication system from the master or IED sending data values to it. The RTU or host system translate and scale this raw data into appropriate units such as the quantity of water left, temperature in degrees, or megawatt before presenting the data to the user via human interface. Digital outputs. RTU may drive high current capacity relays to a digital output board to switch power on and off to devices in the field. The DO board switches voltage to the coil in the relay, which closes the high current contacts, which completes the power circuit to the device. RTU output may also consist of driving a sensitive logic input on an electronic PLC or other electronic devices using a sensitive 5 volt input. Analog outputs. While not as commonly used, Analog outputs may be included to control devices that requires varying quantities, such as graphic recording instruments. Summarize or process data quantities may be generated in master SCADA system and output for display locally or remotely wherever needed. Next is software and logic control. Modern RTUs are usually capable of executing simple programs autonomously without involving the host computers of the DCs or SCADA system to simplify deployment and to provide redundancy for safety reasons. An RTU in human an RTU in a modern water management system will typically have code to modify its behavior when physical override switches on the RTU are toggled during maintenance by maintenance personnel. This is done for the safety reasons. A miscommunication between the system operator and the maintenance personnel could cause a system operates to mistaken enable power to a water pump when it is being replaced. Maintenance personnel should have any equipment they are working on disconnected from the power and locked to prevent damage and injury. The last block from the RTU is communication. An RTU may be interface to multiple master stations and IEDs with different communication protocols, typically RS-232, RS-485, RS-422 or Ethernet. An RTU may be supported standard protocols modules like IEC 60870, ICCP, IEC 61850, etc. to interface any third-party software. Data transfer may be initiated from either and using various techniques to ensure synchronization with minimal data traffic. The master may pull its subordinate unit master to RTU or RTU to IED for changes of data on the periodic basis. Analog values changes will usually be reported only on changes outside a set limit from the last transmitted value. Digital values observe a similar technique and only transmit groups when one included point changes. Another method used is where a subordinate unit initiates an upgrade of data upon a predetermined change in analog or digital data. Complete data transmission must be performed periodically with either method to ensure full synchronization and eliminate stale data. Most communication protocols support both methods. Programmable by the installer, multiple RTU or ID may be share a communication line in multi-drop scheme as units are addressed uniquely and only respond to their own pool and the commands. The applications for RTU are in oil and gas pump stations or in pipelines, network of pump stations, environmental monitoring system, mine sites to air traffic equipment such as navigation aids, remote monitoring and control of functions and instrumentations for hydrographic, water supply, sewage management system, electrical power transmission networks, natural gas networks, the biosphere projects. The second topic from this module is intelligent electronic devices, that is IED. We are going to see them in detail here. The hardware for protection and control is developed and manufactured using most innovative microprocessor technologies. The embedding of software into the device make them intelligent. The term IED is now worldwide used for this technology. The principal hardware scheme of the figure it is shown here. The input side requires the analog values and voltage and currents in synchronization sample. binary processor signals, request from the integrated human machine interface, that is IHMI. The instantaneous analog measured samples have to be converted into digital values for further processing with the microprocessor system. The microprocessor system performs on all enabled functions in accordance with the parameter sets. An example for processing is given in figure 3. That is, here we can see in figure 3 upper side flow diagram, that is analog input CTs versus PTs. Then analog to digital conversion is there. Then fault detection, if it is there, then start protection algorithm. If it is not, then routine program. And after detection of a fault, output signals on contacts, communication interface, and IHMI. If the processing of the input data in MP system detects the need for impact on primary processes, then the appropriate signals are provided at the interface of the IED. That is binary output for commands, analog output for target values, then LEDs for signaling events and alarms, serial interfaces to the SAS system, that is to remote SCADA system or the locally connected PCs. Integrated display for local visualization. So here in this figure, the all front panel display stubs are shown. Now these are the tasks which IED performs, like data collection and archive, monitoring and control of bay topology, initiating the control commands, interlocking, event logging, measurement, presentation in records, tables, diagrams, automation, regulation, communication interfaces, multi protection functions, protection related functions, auto reclosing, synchro check, fault locations, fault recording. The user functionality can be configured by enabling or disabling functions and parameterizing the enable functions. The configuration change is possible by using the IHMI with keyboard and the screen. Preparing the parameter set on PC and downloading the via integrated interface. Remote communication of parameter set from the external terminal or the substation IC. Parameter set switch initiated by internal from the programmable logic or external request. For convenience and efficiency, the PC is normally used to engineer and set the parameters. The second PC function is to present information in the form of tables, log, diagram, records, and the scheme. The IED vendor offer special PC software for this purpose. The changing of functions and parameter sets may also the perform in real time or integrating programmable logic which is engineered on the PC and can be downloaded from there. Now here figure shows the from the left to the right three views on the PC, the linking of functions with the programmable function chart in A section. Then in B section, the presentation of required measurements in an instantaneous value record and in a vector diagram. And in C section, the presentation of actual measured RMS values, identical view on various levels. The functional chart allows the linking of external input signal or internal conditions with internal functions to produce output signals resulting in logical combinations. The output may be a switch command or start of a switching sequence, transformer tap change command, change of target values or voltage control, change of the parameter set. The presentation of instantaneous values in a record and vector diagram offers a complete analysis of various aspects evaluating harmonics, unsymmetry, voltage sag, and equipment stress. The presentation of various RMS values is possible in various overviews at all possible levels: IHMI, local connected PCs, substation control IPC, remote terminals, etc. Current voltage, active and active power, frequency, cos phi in general are also measured. The average values of line and neutral current and maximal achieved currents. The current line to ground voltage, line to line voltage and line currents. The PC support this new flexibility in the function design and event analysis in the convenient and efficient way. The next part from this module is phase measurement unit after IED. Wide area monitoring systems are based on accurate measurement of voltage, phase angles, current, frequency sag and reactive active flows by phasor measurement units installed in selected nodes of the network system. The innovative ideas of this method consist of analysis of multiple real-time measurements from the widespread nodes acquired at exactly the same moment at a phasor data concentrated as shown in figure. This is the PMU principle. This is how PMUs look like. The PMU are based on the digital ID technology and may also contain the fault recorders and further protection functions. The PMU form timestamp measurement set and communicate these packages to the phasor data concentrated with high-speed communication channels using an IEEE standard protocol with a delay of 20 milliseconds. The measurements will be refreshed in time interval between 20 and 100 milliseconds. The phasor data concentrated is normally installed at the network control center and performs the network condition analysis comparing the received measurement sets from different nodes of the network. To achieve accuracy in comparison and suitable analysis results, the measurement have to be acquired with the high time accuracy. If the normal sampling interval of protocol device of 1 millisecond is used for synchronization, an angle difference of 180 may occur. This is not suitable for the stability analysis. The time synchronization by satellite with an accuracy of 1 millisecond will be necessary. With a suitable software solution, the information coming from PMUs supports the dispatcher of the network in being aware of stability situation in the whole network. This helps them to make the right decisions, even in critical situations. In some cases, automatic initiated operations like a fast reactive power injection are started as a countermeasures. Then the WAM extends the level of its functions to wide area protection, which is special form of the system protection. The result The results of the phasor measurement analysis by the data concentrator provides a real-time state estimation and stability observation of the networks, the detection of power oscillations, their analysis and the generation of appropriate countermeasures, the dynamic load flow control, improved accuracy of the analysis of faults and fault location, the monitoring of asset condition for their higher utilization. Now here, this figure represents the jump of the voltage angles between the nodes A and B. After the outage of 1000 megawatt power station in node A, the distance between node is over 600 km. The subsequent fast damping of oscillation identifies that this outage is not dangerous for the stable network operation. WAM systems are widely introduced in transmission system of continental Europe. The application in distribution system is under consideration and first pilot project have begun. The interactive user interface of the data concentrated has to be designed to provide an optimal support to the dispatchers. The following design rules are common in advanced WAM systems of different vendors. The fast identification of system conditions, free selection of desired measurement records or phasor diagram in configuration field, setting of threshold to be observed, simple shift between online and offline modes for the interactive analysis of events, geographical presentation of the network with allocation of PMUs, allowing the fast location of areas with stability problems, gateways for data export and import to allow the operation with other assessment tools. Now, in this figure, an example of display applying the above mentioned features is explained. The installation of about 50 distributed PMUs in the whole ENTSO interconnected network of continental Europe allows the fast identification of emergency situation, stability problem, and congestion in partial control areas. So the first part indicates here the state of the power system, and second is selection of online view or historic view. Third indicates geographical display. Fourth, measurement records. In fifth and sixth are event report and phasor diagrams. So friends, here in this module, we have seen remote terminal unit, intelligent electron devices, and phase measurement units. For this module, your assignment questions are on your screen. Thank you very much for listening. And if you have any query, you can write to me on somnath.hadpe@yahoo.in. Thank you.